Hello. Now that we have spoken about in previous classes, we spoke about the damaged brain in the context of cerebrovascular disease and in the context of aphasia. Now we are going to speak about repairing the damaged brain, and that is Kandel Neuroscience, Principles of Neuroscience, Chapter 57. So most of the presentation is based on that chapter. You can refer to it, and also the summary that I have provided you. Looking first at how neurology and neuroscience work together. Neurology, of course, is a clinical field, and it looks at neurons and how they behave and how the nervous system is structured and how it functions. And it also is concerned with the diagnosis of neurologically based diseases or neuropathology. Pathology means disease. And looking at how to treat these disorders. So the majority of neurological disorders so far are not curable. And what neurologists do, they know how to diagnose, and they do a great job diagnosing these disorders. And the technology, of course, has made the diagnosis much more, for example, accurate. We know more about these disorders. The neuroscience component, which is focused on studying how the system works and finding ways for clinical practice and to drive the field of clinical practice. In terms of the neuroscience component, the developmental neuroscience has contributed largely to the discovery of how the brain is repaired after, and the nervous system, how they are repaired after injury. So we are going to explore some of these ways and look deeper into the brain on the cellular level and see how recovery is possible. So first, in terms of developmental neuroscience, it has contributed in three different ways. The scientists, have been studying what goes on as the brain and the nervous system develop. And they're trying to understand the diseases themselves. But one way is also to look at the treatment options. How do you prevent, for example, brain damage? How do you replace damaged neurons? How do you preserve areas that could be salvageable? For example, some examples that we would cover in terms of areas that could be, say, for example, salvaged. If someone has a stroke and we said there's a focal area where the stroke is, that is called an infarction. Around it, there is a penumbra, which is the area that is, is vulnerable, very vulnerable, and ischemic. And if you don't intervene immediately and provide a solution, that area is going to become infarcted as well. It will die. So the focus on studying how to preserve and how to replace the damaged neurons, for example, has led to the understanding of how nerve cells actually can be regenerated and how the peripheral nervous system itself regenerates neurons after injury. And the other thing that developmental neuroscience has contributed is that our understanding of how the axon itself develops and how the synapses are formed and how, for example, they communicate, the neurons communicate. That has led to advances in terms of cell regeneration. In order to be able to treat and cure and so on, you have to first understand how the system works. And the third aspect is that basically looking at neurodevelopmental disorders, increasing research is showing that these disorders happen very, very early, and in some cases in conception, and in some cases during fertilization, and in some cases during various stages of the embryonic development stage. So focusing on this and trying to understand how, for example, disorders like autism or schizophrenia, how they develop and affect the system, that has contributed significantly, and eventually it will contribute to discovery of how to cure or how to treat these disorders more effectively. So again, the idea is we have to learn how the system works and how it develops, and in the process that will enable us to understand how the treatment is and how the system can be stimulated to regenerate. The structure of axons is, by nature, it makes the axon vulnerable. The axon is simply like a tiny thread, and it's very, very, very small. So when there is damage to the peripheral nervous system or damage to the brain, almost always it involves shearing and cutting of axons. So once you have an axon and you, for example, sever it, let me show you. Once it is severed, immediately you disrupt its function. It cannot communicate with the other cells that it usually communicates with. And there are some neurons that communicate with 10,000 other neurons, or receive signals from 50,000 others, or send signals to thousands of neurons. So we are speaking about, for example, one neuron can have an effect on many, and especially when we speak about, say, a whole area dying, we are speaking about a large number of neurons. So when a neuron is severed, we have, let me go back, sorry. We have two segments. We have a segment that is still attached to the cell body, to the axon hillock, and a segment that is away. And that segment that is on the other side, of course, we call it the distal segment, and we call the one that is closer attached to the cell body the proximal, because by definition, proximal means, close to the body. So when we speak about these, they will be affected differently. Each one is going to undergo a certain degeneration process, and then we are going to also speak about what happens to the cells, the neurons that communicate with the cell body of the dying neuron or the damaged neuron, and what will happen to the neurons or the cells that receive signals or depend on their information. They depend on the synaptic terminals of the severed axon. So again, 4 areas that we'll be speaking about: what happens to the neuron itself, the two pieces that it has now, the severed piece, the distal and the proximal, and then we'll speak about what, the areas or the neurons that receive their signals from the proximal terminals, of the proximal piece, and neurons that send their signals and they connect with the cell body and the dendrites of the damaged neuron, of the one that is where the proximal segment is. So what happens immediately after the neuron is, the axon is severed? You have this distal segment with the myelin around it, and it has its own synaptic terminals, and it's still connected with the target cells that it communicates with. And then you have the other segment, which is the proximal segment. immediately the distal segment it begins to disintegrate, and the skeletal framework of that segment, that the tube that makes the axon, for example, it is supported by a cytoskeletal framework that keeps it open, and it gives its shape. That starts to be dismantled. So when you have this on a large scale throughout the axon, that is going to make it, atrophy. The proximal segment undergoes more significant changes because it's connected with the cell body, and the cell body itself is going to undergo significant changes, a process that is called chromatolysis. So first, that segment, the proximal segment, begins to shrivel as well, like the other side, and then the cell body itself now is going to start to undergo apoptosis. As I explained, apoptosis means spontaneous self-death for a cell. When the body has 60 trillion cells. Of course, everything at all, including neural cells and everything. And every single cell, has its own signals inside. And if you go outside, for example, in the sun, and it is a hot day, a lot of cells in your body are going to die because the sun is going to alter the sequencing of the DNA, and when it is altered so much, it is going to be dysfunctional. And then if it can't repair itself, then it immediately starts to trigger apoptosis. It will kill itself. What will happen if the cell doesn't kill itself? When it is too damaged, that is what we know as cancer. It is going to multiply, and it's, the one that produces other cells that are also damaged, and it keeps multiplying out of control. And that is all it takes is one single cell in these 60 trillion cells to go like that, and the person gets cancer. So apoptosis is very important, and cells that are damaged beyond repair are going to undergo apoptosis. So the process involves first gradually chromatolysis, which is basically dismantling the basic foundation of the cell. And we are speaking about this process given, for example, if no intervention, if the system doesn't provide any preventative measures. We speak about it first, and then we speak about what the process looks like and what preventable measures are put in the peripheral nervous system, and why the system chromatolytic or chromatolysis is allowed to go on in the central nervous system neurons. So this is general again, and we'll come back to it and see how it works in the peripheral nervous system and how it works in the central nervous system. So first, let me show you here. The cell body itself, it starts to gradually degenerate, and with it is the signal that is, the proximal segment. But the cell body itself, it's the nucleus. It has to be in a particular location. The nucleus then is squeezed out, and you could see it shrunk, and it is squeezed out of its normal place. That is going to have a huge impact on how the nucleus functions, how it relates and communicates with the organelles around it, and so on. So that will remarkably alter the function of this, the cell body. In addition, you are going to have the endoplasmic reticulum is going to be defragmented. And this is a structure that, if you look here, it is surrounding, in proximity surrounding the nucleus, and it is part of the system to maintain and produce materials, spare parts to repair damaged cells and to make new cells and so on. So the DNA itself, the genes are not going to be able to function the normal way. They'll be shuffled and transformed in a way as to make the cell dysfunctional. And then these changes now, if they are allowed to continue at this level, and there's no intervention, for example, in the central nervous system, these changes are irreversible. And of course, that in the central nervous system, it will definitely lead to cell death. In the peripheral nervous system, when chromatolysis occurs, if it occurs in a time where the intervention doesn't come in, then these changes will be irreversible even after the axon itself regenerates. So ideally, you want to have the axon regenerating and then faster enough before the chromolytic changes start to stabilize. So now, what is the effect on the nearby cells? Now, we spoke about what happens to the distal component of the axon, what happens to the proximal and the cell body. Now, looking at the distal segment and what it communicates with. So first, I was speaking about the peripheral nervous system, what happens there. The Schwann cells immediately, as soon as the severed neuron is severed axon is identified, immediately the Schwann cells, they start to degrade the myelin sheath. So the myelin itself around the severed axon starts to degrade. And I'm showing you a motor neuron, which is part, of course, of the peripheral nervous system. So Schwann cells, when we speak peripheral, means Schwann cells. So the Schwann cells also deploy white blood cells, macrophages, to remove the debris that is, the debris comes from the destroyed myelin. And then the Schwann cells also stimulate growth factors to induce the cell body to regenerate. And this is how recovery occurs in the central and the peripheral nervous system. As I explained, more than 80% of the damage, in 80% of the cases of damage to the peripheral nervous system, the system regenerates and it will repair itself. And the Schwann cells play a critical part in that repair process. They drive that repair process. So they stimulate the growth, growth factors to induce the cell body to regenerate a new axon, and new axon is going to eventually, either go and connect with the other severed piece or find another target to connect with. Or in the central nervous system, we have the oligodendrites. They are the cells that do the myelination. And in that case, the oligodendrocytes, they have no influence on the regeneration process. And they are not as influential as, for example, the Schwann cells. So in addition, the blood-brain barrier prevents entry of more macrophages. The brain has a limited number of these that we know as the microglia. But you cannot get more from outside, from the bloodstream, because macrophages in the bloodstream are large. And when they are not allowed, they cannot go through the blood-brain barrier. So that's a limitation that leads to a slow degeneration process, when there is damage. It takes a while for the process, for example, the degeneration, to kind of take place, and because also the cleanup is limited because the microglia are the ones to do the cleanup, and there's a limited number in there. So at the same time, in addition to these changes, there are inhibitory factors to prevent regeneration in the central nervous system. So what happens now to the cells that are connected with the severed axon, with the, say, for example, the terminals of the severed axon? You know that the terminals communicate with cells. We call these cells the postsynaptic cells, the ones on the other side of the synapse, between the severed neuron and the neuron that is receiving signals. So what happens now is the neurons that are synapsing with the severed axon, they do not get the stimulation. They do not get any communication from that neuron anymore, from that axon, and they begin to shrivel. Because if you do not continue stimulating and firing, and then that is going to cause the shriveling of these neurons, or the atrophy, best known, the term. And then they become ineffective, and their signals will be weak, and as a result, they are not going to be able to send signals to the next set of neurons that relies upon them. And these ones, in turn, will not be able to get the signals, and it keeps going on and on, exactly like the domino effect, which is going to eventually lead to a malfunctioning of the entire circuit. So it can malfunction partially, it can malfunction completely, based on the number of neurons that are affected and how severe and significant the damage is. So the effect on the cells that are sending signals and are synapsing with the dying cell body and the part of the axon attached to it, these are influenced and affected in a different way. And on any given cell body, you have a number of axons making connections. And also on the dendrites. Most of these, of course, synapses are on the dendrites and the dendritic spines and so on. So the first effect, as soon as the process occurs, is for these neurons synapsing on the cell body and the dendrites is to withdraw. They will break down, they take back or withdraw their synaptic terminals. And as a result, all the synapses with that particular cell are now severed. Because the system detects that it is now no longer able to transmit signals. So it's useless, and the brain is going to invest its energy somewhere else. So this is a process called synaptic stripping. Synaptic stripping. The synapse is made like this. Now you just tear it apart by withdrawing the synaptic terminals, take them away, and then that cell body is going to be by itself. It is not communicating on either end with any neurons, not at this point. So this would be the case in the central nervous system, where the cell actually just is destined to die. But in the peripheral nervous system, as we shall see, it will be different because of the recovery process that is directed by the Schwann cells. So the result of this death of the cell, the result of the synaptic stripping and isolation of that cell, now it is not communicating with any other. On the severed end nor on the synaptic, on the cell body and or the dendria. So that impairs functional recovery. What does it mean to say functional recovery? Is the ability of the brain to exert, say, for example, effects on the body parts to make them move, to make them perform certain functions. So when we say functional recovery, that will be impaired because the person will not be able to get these damaged areas to do the functions that they were used to do. Now let's look at the process of regeneration, axonal regeneration. So there is a difference between the central nervous system environment and the peripheral nervous system environment. And the environment determines which process is going to continue to recover, to regenerate, which process will continue to degenerate. And again, in the central nervous system, and the spinal cord and the brain, the process, especially in the brain particularly, the process is irreversible, and there is no regeneration. Basically, if there is, it would be very negligible. But in the peripheral nervous system, more than 80% of the cases of neural damage get repaired. And for example, there's, the clear and facts of everyday life that we see around us that show peripheral regeneration is when someone injects Botox. Botox is a toxin. It is a neurotoxin. It kills particular areas of neurons and axons and stuff like that. So it is measured, of course. For example, someone would like to prevent the muscles here from contracting, going like this to make certain expressions, or because of the sun or whatever. So these areas where, the muscles that are able to do that, you have the injections, and that kills the neurons, the nerve fibers that innervate the muscles. So now the muscles are not able to do anything. However, in 6 months, almost exactly by the day, you are going to see that the neurons now have repaired their synapse, their axons. They have regenerated them. They are able to reconnect again and connect with the muscles, and they are able to move the muscles again. So guess what? The person has to go back for another injection every 6 months. So also another example is breast cancer. When someone has a breast cancer and one breast is removed and there's an implant, they will tell her that you are not going to have any sensation now, of course, because of all the stuff that was removed. However, in 2 years, you will start to get the sensation back. Why? Because the neural the nerves start to grow at a certain distance every month and every year, and in 2 years, then the entire tissue of the skin covering that artificial breast, that will be innervated, and the woman is able to feel again in that area. It should have sensation and so on. So that these are examples of peripheral regeneration of the neurons and nerve fibers. So the process is quite robust in the peripheral nervous system, and in the central nervous system, it is hardly existent. When the axotomy occurs, remember, axotomy is severing an axon. The process begins, for example, by having the initiation starts with the cell body, and there's stimulation of that segment that is still connected to the cell body, to the axon hillock. It starts to re-sprout. It begins to extend, to grow a little bit more, and to actually, start to make, to search for the other end, for the proximal end. And it continues to go. It will be guided by growth factors induced by Schwann cells. So to be able to find its target, because there are molecular signals on the proximal end and molecular signals on the distal end, and they are known to kind of find each other and match each other. So in the spinal cord, for example, when a piece, an area dies, then that's part of the central nervous system, the descending, the area above the damaged site, the axon coming down and above the damaged site, is going to kind of go around the damaged site and will find the way to reconnect back to the other part of the peripheral nerve, or the axon that is part of the peripheral nerve that is now damaged, that is now disconnected. It will find its way, and then it will reconnect with it again. One of the things that makes this possible is that when the axon is severed initially, there is connective tissue surrounding it, and that connective tissue helps it, stay together and so on. That connective tissue, if it goes away, if it also dies, then that regeneration process wouldn't be possible. That doesn't happen. That connective tissue also dies in the central nervous system, but it doesn't die in the peripheral nervous system. So it aids, because it is still, connective tissue is still living around the distal stump that's above the injury, above the cut. That is going to be part of the initiation of the regeneration. It enables the neuron to start to heal. So the proximal stump above the lesion sprouts new axon, and it extends it, and it starts to find the other piece and to connect back with it. So this takes the regeneration process, of course, looks differently based on what kind of neuron you are speaking about. For example, number one, if the neuron is a motor neuron, the motor neuron, of course, what does it insert onto? Muscle fiber. So once it is repaired, it is going to start again to try to reconnect back to the same muscle fiber. But for any reason that makes it impossible, it's going to find another location on the muscle fiber to connect onto it. Sometimes it doesn't find its target. Sometimes some of these axons, as they try to locate a target to land onto, to insert onto, they just lose their way, and they fail to reconnect. So, but the majority, of course, they manage to connect back. The sensory neurons, what do they insert onto? What do they, where do they get their information and so on? They insert onto the skin, as the example of the, breast cancer I mentioned, or the Botox. So this will go back and reconnect back to the same areas. In terms of the regeneration of the autonomic nervous system neurons, what do these neurons look like? What do they specialize in? There are, in autonomic, they specialize in activity that you have no control over. For example, blood vessels that need to dilate and contract. Now, these autonomic nervous systems neurons, when they are fixed, they go and reconnect on the blood vessels and activate them. Where also they connect and surround the pouches where the body stores its hormones and its chemicals that it needs to regulate chemical reactions in the body. So we call these pouches, we call them glands, like your earwax glands, like your pituitary gland, your thyroid gland, and so on. So these again go and reconnect. But in terms of now looking at the axon and how I explained how it would heal, getting the proximal segment that's still connected to the cell body, it will sprout and it starts to grow, kind of extend the axon to grow another axon, and it can either continue to look for its target. If it finds the severed piece, it's going to reconnect with it. If that doesn't exist, then it will continue to grow, and it will continue to grow synaptic terminals, and it will find its new connections to make. But now let's say the neuron that finds its target, its severed piece, it goes back and grows and grows, and it's guided by Schwann cells, and it finally reconnects. As you see here on this image. So now here is an intact neuron, and then it is severed, and now it starts to sprout new extensions. So, but in the process, what happens to myelination? Myelination will begin to regenerate. If there's no myelin, for example, the myelin has already died because of the damage, then Schwann cells will induce the formation of new myelin, a new myelin sheath. It could be a completely new, or just the pieces that are damaged beyond repair, they will be replaced. So in any shape or form, that neuron is going to end up getting back its myelin sheath, and it will be going back to perform again. But if the damage that takes place, if the repair of the myelin sheath occurs before the chromatolysis process and the shriveling of the cell and so on, that is going to be, ideally the neuron will function better. However, if the chromatolysis process is not reversed, or if it continues, for a little bit longer before the myelination, that process is not going to be reversed. So yes, the cell is going to have a new axon. It will have a new axon, myelin sheath, and so on. But the cell body itself is not 100% as it used to be in terms of, the function. In the case, again, if the process of chromatolization continues for an extended period of time before the repair. So you can see it again here. It's reconnecting, and then eventually the damaged pieces of myelin get repaired, and then but you still have the process in that case of chromatolysis is being reversed. But if again that occurs earlier and it stays longer before the repair process begins, that chromatolysis effect cannot be reversed. And then this, when we say the two conditions, one exists almost exclusively in the central nervous system, and the other condition where you have full repair and reversal of the chromatolysis, it's in the peripheral nervous system, but that process doesn't always occur. The complete repair doesn't always occur because many of these cells anyways end up dying. They are severed beyond repair. So as we will learn, as if you go back to the summary of the chapter, the details, you will see that. So now, how does the process of regeneration occurs? What prevents the process of regeneration to occur in the central nervous system? I said before that the environment is the main determinant, and the environment in the peripheral nervous system is conducive to the regeneration process. In the central nervous system, it inhibits, it's not just conducive, no, it inhibits and prevents the regeneration. So, the reason is in terms of the inhibition. And again, I've just mentioned it briefly here, but you go back to the summary and you see why exactly, and you need to understand why. So this is a very important process. The inhibition process occurs because of signals that are induced by the myelin. As soon as the myelin, for example, let's go back to the severing of a neuron. A neuron is severed, and then now you have two pieces. The distal, the proximal segment connected to the axon hillock of the cell body and the cell body. The other piece is the distal, and recall again. Keep in mind, in the central nervous system, the myelination is formed by a different kind of cell, the oligodendrocyte, and that cell works differently, and how it makes the myelin sheath, it works differently. Go back, please, to the previous chapters where we discussed the formation of the myelin sheath, and you need to know in this context again how this cell behaves and how it forms the myelin sheath. So you need to connect this information. So now we have a severed axon, and now the actual degeneration process is now allowed to continue to its end in the central nervous system. However, the only difference is, of course, nothing is going to stop it, and there are things to make it continue and also to prevent regeneration. So you are continuing the process of degeneration and preventing regeneration. So the first thing that occurs is the same process for the distal end, where the whole piece of the broken axon is going to start to go into atrophy. It is not communicating now, getting signals from its original from the body, and the myelin sheath is going to start to be degraded. It will fall into pieces. And as soon as these little pieces just fall apart, that activates signals, and that will trigger the action of the microglia to start to clean up. But that is a process that is slow, because there are less microglia in the brain, for example, and the central nervous system than in the peripheral. So once they start to to degrade the myelin, in that degraded myelin, there are signals to prevent regeneration. So there are other parts of the, other cells, for example, the astrocytes, they are going to get signals from that to say, you go and suppress the aspect, prevent anything from regenerating. So the process is slow, relatively slower than the degeneration process is relatively slower in the central nervous system compared to the peripheral. And the reason again is because of the limited number of microglia inside of the brain. And we know you cannot get any macrophages in through the brain bloodstream because the macrophages are big and they cannot get in. So that makes the process of degeneration slow in the first place. And also, again, as said, the signals for degradation are just triggered simply by the pieces that are falling. When the system recognizes that it is the severed neuron is starting to lose its myelin, it just induces the signal to prevent any regeneration. And there are reasons, it is detailed and explained in the summary. Go back and know exactly step by step why this, how and why this occurs. Let me pull the file and we'll go over it to make sure that there is no misunderstanding of this. Okay. So here, in terms of the central nervous system environment itself, there are two major reasons that prevent the regeneration process, and that again, the central nervous system environment has some growth factors that actively inhibit the process. The first one, for example, is that the fragments of the myelin that is degrading contain several inhibitory agents that prevent any regeneration. And then the second one is the scar tissue that forms during, in the process. When any part is damaged, then you start to get, the system starts to try to repair it by bringing in more blood, by bringing in more immune system, mechanisms. But in the process, in order to do that, you have to dilate blood vessels, you have to make more of these branches and so on. So that now makes quite a web of these tissues, and that often remains after the injury. So that is called scar tissue. So it limits the size, and of course scar tissue, the benefit of it is it limits the size of the damage, and it tries to re-establish the blood-brain barrier in order to feed the remaining part of the neuron, and to reduce inflammation. But that in the central nervous system, that doesn't prevent the dying neuron from dying, and it limits the damage a bit. But the scar tissue itself is one piece that contributes to the prevention of the regeneration process. It prevents further damage, but it doesn't stop the death and loss of these neurons that have already been severed. Now, interestingly, if axons are severed in the embryo, that damage is reversed in a similar way and in a strong way as equal to the peripheral nervous system regeneration process. So age is a factor. Again, embryonic means the embryo is inside of the womb. It hasn't been born yet. So if there is, say for example, down the road, if they discover how to operate on the brain of an embryo, before you open the mother's belly and get out the the fetus and try to operate on that brain, that could reverse, for example. But in any case, that is again the only condition, the only situation where peripheral nervous system, central nervous system neurons are able to regenerate and to heal again in a certain, just similar to the peripheral nervous system. That only happens in the embryo before birth. So now, obviously, the peripheral nervous system has three things, three functions, three types of neurons in terms of physiology, in terms of function. They can be, we are speaking about peripheral. The nerves that are the cranial nerves inside of the skull that innervate the face and the neck and the shoulders, and one of them innervates the inside of the trunk, and the spinal nerves that come out to innervate your arms and your legs and the sides of the body and so on. So there are three types of neurons, based on the function. We have the motor system that has motor neurons. And then we have the sensory system that has sensory neurons. And then we have the autonomic nervous system neurons, which mediate or control functions that you have no control over, like stomach, digestion, blood vessel dilation, heart, beat, and so on. So again, motor, sensory, and autonomic. So we said in the peripheral nervous system, these are able to perform because they have to do either with motor or sensory. The person, 80% or more of the cases, get the functions back and the system is repaired and so on. But in the central nervous system, these central nervous system neurons, they do not regenerate. So that process of regeneration is not a big factor in terms of how we get back some of our functions. What enables someone who has a stroke, for example, to get back some of the functions he or she lost before the stroke? What enables the healing? What enables functional gains after? So the central nervous system relies on a different mechanism. First, neuroplasticity. Neuroplasticity is the ability to reconfigure connections of the brain. The ability, for example, you have a connection now here, and that connection is no longer working because on one end it was lost. The source that is giving the signals, for example, a neuron, dies. Now you have this neuron waiting, and there is no information coming from this. It's not going to sit there just hanging, doing nothing. It will find another neuron to connect with. It will find another target. That is called rewiring. That is called neuroplasticity. So the brain's ability to reconfigure its networks, its circuits, to reconnect again, that is neuroplasticity. And one of the powerful forces driving neuroplasticity is neurogenesis. Neurogenesis is an entire field that started after 1997 or so, on the discovery that certain areas of the brain are able to regenerate, to produce new cells. We know a cell dies in the central nervous system, the cell dies, it doesn't get back. However, you get cells to replace it in certain cases. And these two areas in the brain that are known as the only two areas where neurogenesis is possible are, number one, the olfactory bulb, which is the some kind of a nerve that goes on and inserts onto the roof of the nasal cavity, and it gives you the ability to smell. It sends extensions to line up the entire roof of the nasal cavity, and these extensions sense the food and whatever you have in your mouth is going to evaporate, and it will be embedded into these pieces of the olfactory nerve basically, and that will be chemically analyzed to make you identify what you are eating because of the smell. More than 80% of taste is smell. So this is one of the areas where, as gradually every day we lose neurons there, but every day we continue to regenerate. To get new neurons born to travel and to be embedded to replace the dying neurons in the olfactory system that enables us to smell. So that's one area, again, where new cells are born, where neurogenesis is born. The other one, interestingly, is related to memory learning, and that is in the hippocampus, particularly in the dentate gyrus of the hippocampus. And there are also areas around the hippocampus that also have that component, but these are the only two areas where there's neurogenesis, again, in the olfactory bulb and in the hippocampus and a couple of areas around it that have to do with learning, with memory. And this is how and why we are able to continue to learn new things. So the process of neurogenesis is a powerful force that makes neuroplasticity possible, that enables the brain to rewire, reconfigure its connections. So one member of the circuit is not working. Now let's bypass that person, sever the connection, go connect with another circuit that can enable us to have an access to, for example, to information or to processing in a different way. So in many cases, that enables us to get back some of the functions that we lose, but it depends on the level of the damage, the extent of the damage, how long the damage has been there. And the process, there are sensitive periods. Number one, these sensitive periods for neuroplasticity, for example, the highest it is in the early stages of life, and it basically in the first three, before birth, of course, and it continues to the first 3 years, and to some extent it could even go up to 4 or 5 years, but definitely the first 3 years of life are the biggest and most important and most robust periods of neuroplasticity, where the brain is so flexible to the extent that if one person loses half or an entire hemisphere, the other hemisphere can be induced to take over and to perform the functions almost with little impairment. So then the second period where neuroplasticity is very powerful or the second time, is when there is injury. As soon as injury happens, it starts to immediately induce the process of neuroplasticity, where the parts of the brain, the neurons that have lost their connections now, they try to just look for new targets and try to reconnect again and reconfigure themselves again. So now we call this process spontaneous recovery, when someone starts to get some of their functions back. And research at least is showing us now more evidence that when we provide intervention, like the therapy that you provide immediately after injury, is going to expand the process and the scope of spontaneous recovery. It enables the person to get, more, because neuroplasticity is induced, and the more that you aid it, the more expansive it is going to be, and the greater its positive effects, are gonna be. So that again justifies why we should provide treatments directly, as soon as damage occurs, to facilitate that process. Like someone swimming, toward the shore, and as they are swimming, actively at a certain pace, then you have a big wave comes in the same direction, and it just gives them a big push. That big wave could be the treatment, the creative treatment that you provide. Of course, science is still, just in its infancy, science of the brain, and new ways are being discovered, new ways of, instruments and imaging and so on are being discovered. It's very exciting, and they're even, starting to work on implants, like retinal implants, to make someone regain their sight. For example, certain stimulation, kinds of neural brain stimulation, like deep transcranial brain stimulation, to enable people to get back some of their functions and so on. Again, please go back to the chapter to read more about this, and to the chapter summary to learn more about the technology that we kind of might be using. Some it is being used today, but there are many promising uses of technology. It is they presume that in a few decades that you'd be able to implant a memory chip, for example, with it has an entire dictionary and so on. So please take a few minutes to watch this video, and that will speak about the technology, and it will show you, for example, I found it interesting that you can actually control someone's to have your brain control someone else's movements, and it's almost funny when you see the video where the young woman is moving her hand, and then the guy whose arm is connected with her brain is also moving as a result of her intended movements. Actually she is performing the movement, and he, out of control, he doesn't have the gun, and he starts to move his hand, and it's really insightful. So enjoy the video, and I hope that you have written good questions, and in case you have any questions, and also maybe make a quiz for yourself based on these slides. Thank you.